Have you ever imagined the ground shaking beneath an entire city? So homes and buildings collapse in moments, while skyscrapers remain standing. How do towers of steel and concrete withstand devastating earthquakes, while buildings much smaller than them fall as if they were made of paper? What is the secret that keeps a tower weighing thousands of tons from collapsing, but instead makes it sway, bend, and then return to its place again? In this journey, we will not only search for the secret of survival, but we will reveal how skyscrapers are made from the inside and how steel and concrete turn into an intelligent system that resists one of the most violent forces of nature. When towers dance instead of collapse, skyscrapers are designed to interact with earthquakes instead of resisting them. Instead of becoming rigid, they transform into a flexible entity that absorbs the shock and redistributes it. This concept clearly proved itself during the Chile earthquake in the year 2010, which reached a magnitude of 8.8, when around 2,000 high-rise buildings were exposed to ground acceleration that exceeded the limits. And yet, only 50 buildings required major structural intervention, and only 8 deaths were recorded inside these modern towers, with a survival rate exceeding 99%, meaning that destructive energy was transformed into calculated movements that pushed the points of weakness away. Behind this success stands a complex system of smart technologies, such as massive tuned mass dampers that move against the vibration of the building, and base isolation systems that separate the structure from the ground, and viscous fluid dampers that absorb energy the way a sponge absorbs water. In addition to rigid external structures, these systems regulate movement and control it. And we see this clearly in the Gran Costanera Tower, which withstood a massive earthquake during its construction without any structural damage. Modern towers have become more like intelligent systems that absorb the shock and redistribute it instead of breaking under it. When engineering becomes a shield against disasters, when looking at the tallest buildings in the world, such as the Burj Khalifa, we realize that earthquake resistance has become an essential part of the design from the foundations. Thanks to the buttressed core system and deep foundations extending for dozens of meters, in addition to ultra-strong materials and energy absorption systems, the building becomes capable of avoiding one of the most dangerous phenomena in earthquakes, such as resonance, for example. It is designed so that its natural frequency does not match earthquake frequencies, keeping it outside the danger zone. And with real-world performance data from countries such as Chile, Japan, and Mexico, and with the development of strict building codes, it can be said that skyscrapers today represent the peak of balance between strength and flexibility, where the goal is focused on making them move intelligently, because movement can sometimes be the savior instead of stiffness and resistance. When the Earth explodes, the fault that waited for centuries, there is a world beneath our feet. We do not see it, even though it never stops moving. Those giant tectonic plates slide very slowly. Sometimes they collide or rub against each other along boundaries known as faults. And there, at those hidden points, stress silently builds up for years, decades, or perhaps entire centuries, until the decisive moment arrives. The fault suddenly ruptures, and immense energy is released in a fraction of a second, generating earthquakes and sending their waves in every direction as if a cosmic shock were striking the surface of the Earth. And this is what happened in the Turkey and Syria earthquake in the year 2023. The disaster came in the form of a violent series of shocks, followed by aftershocks, claiming more than 45,000 human lives. Most of them fell inside buildings that were unable to withstand this sudden violence. The real danger: when inertia betrays you. Imagine that you are driving a car and suddenly hit the brakes. Of course, everything inside it will be thrown forward. This is what is known as inertia. It is the same principle that governs the behavior of buildings during earthquakes. When the ground shakes back and forth, the building tries to stay in place, then begins to move. But it is always delayed behind the ground. This delay generates enormous horizontal forces that deform columns and walls, turning them from their straight form into a tilted shape resembling a parallelogram. And with multiple floors, the disaster becomes more severe because the lower floors carry the weight of everything above them. So they receive the greatest amount of these forces. And if they are not well designed, they begin to collapse gradually. The situation worsens whenever the earthquake is stronger and closer, or occurs on soft soil that amplifies vibrations. And here, the danger lies in the way the building responds to the earthquake. The secret of buildings surviving even if they are damaged. It may be shocking to know that modern buildings are not designed to remain intact, but to keep you alive. Concrete, despite its immense strength in bearing compression, fails under the tension caused by earthquakes. So it cracks and may collapse. That is why it is combined with steel, a material known for its flexibility and its ability to deform without breaking. And during strong earthquakes, steel bends and absorbs energy, protecting the structure from total collapse. Even if the building emerges severely damaged, this is the life safety principle adopted by building codes around the world. But the matter does not stop here. There are more advanced technologies such as base isolation, where the building is separated from the ground by flexible layers that reduce the transmission of vibrations. These systems proved their effectiveness in some hospitals in Turkey that remained standing despite the disaster. And yet, the greatest challenge remains uncertainty, because earthquakes may come stronger than engineers expected, or because human errors and high costs may prevent the best solutions from being applied. In all cases, it is about constructing buildings that give you a chance to live, even in the worst possible scenario. And because steel adapts to earthquakes through its ductility, it can be seen as the last line of defense. Lightweight strength, reducing danger instead of multiplying it. The strength of steel, alongside its toughness, comes from its intelligence in distributing weight. Steel has an exceptional strength-to-weight ratio, meaning it is extremely strong without being heavy. The importance of this point is that the weight of the building itself is part of the problem during earthquakes. The greater the mass, the greater the inertial forces, and the greater the swaying. That is why lighter buildings are less vulnerable to collapse. Here, steel's superiority appears, as it gives you a strong structure without making the building heavy. So it reduces the forces that try to tear it apart during the tremor. In addition, steel's behavior is accurately predictable. So engineers know in advance how it will behave under compression and tension, allowing them to design buildings with calculated responses. But the danger does not end when the earthquake ends. It may begin afterward, with fires caused by gas leaks or the collapse of networks. Here, a new advantage appears. Steel is a non-combustible material, so it does not turn into fuel that worsens the disaster. More importantly, it gives buildings a second chance even after they have been built. Steel structures can be easily modified and strengthened, allowing old buildings to be upgraded and seismic braces or frames to be added without the need for complete demolition. This flexibility means that a building can evolve over time and become safer with every improv, meaning it becomes an essential element in the equation of survival. Why steel excels in the battle against earthquakes? In high-risk environments such as Turkey, steel becomes the most superior engineering choice. As we have reviewed its advantages, it is also distinguished by the consistency of its properties as a result of precise factory manufacturing, making its performance predictable compared with concrete. which is affected by the quality of on-site execution. Modern systems rely on advanced solutions such as moment-resisting frames, which provide architectural flexibility, and concentrically braced frames, which increase stiffness, and hybrid systems that combine both, in addition to BRB braces that prevent buckling and multiply energy dissipation capacity. Technologies such as base isolation and dampers also allow energy to be converted into heat before it destroys the structure. And with the application of global standards such as performance-based design, steel becomes an integrated protection system that balances safety, economy, and the continuity of life after the disaster.